little bit like an outsider when you move here. I mean, everyone's very friendly and like makes you feel comfortable, but there's that little bit of like, oh, you all know each other for 3 generations. Oh wait, no, I wanted that on there. Okay, man, we are sparse today. Maybe those two are just late. Yeah, okay. That clock is long too, or what is the word for that? Fast. That clock is fast. We can hear you. Come on, chop chop. I was like, where is everybody? I know Olivia's going to be gone, but. Okay, so I don't think I'm going to do a whole lot of reviewing here. I don't know. Yeah, I don't think we need to. I think my first class, like, I just never quite have the words perfect. So then I have to, like, review with them more. So let's just jump into doing a practice problem, a set of practice problems here, which is pretty much just applying the manipulations idea, what we do to the K. So you might want to refer back to that summary page to do these. We did do that one though, right? Yeah. Okay. The one thing that really causes problems with my kids is how everyone always has family that they're like having dinner with on Sunday night or whatever, or like family parties on the weekends. They're like so depressed. They're like, why can't our cousins live here? Why can't our grandparents live here?
Is the rest of your extended family still in Texas?
No, that's not even where we're from. So I grew up in the Midwest in St. Louis, and my parents live in Missouri still. But my siblings are like all over the place. Like one in DC, that's the closest. Then like Seattle, there is actually one in Texas, St. Louis, Utah. My husband's from Utah, so most of his family's there. But oh, can you see? Oh, you can. Yeah. Oh, that was the KC. That's why it didn't quite look right. Okay, so just keep in mind that I cannot tell how many digits that's supposed to be. Keep in mind that these are different than when we manipulate Hess's law problems. So when you manipulate, like when you flip around a Hess's law problem, you just change the sign of the enthalpy. There aren't negative K's, that doesn't work, so don't just change the sign. You need to do the inverse, so 1 over the old K. This one was talking about KP, so this is the number we're using, the 2.26 times 10 to the 4th. So that one was flipped around, so we did 1 over that. And then for the second one, that was not flipped, but it was multiplied, everything was multiplied through by 3. So in that instance, you don't multiply by 3, you raise it to the 3rd power. And my calculator did not put that in scientific notation. Does anybody have the exponent there? I could try counting it, but my eyes are terrible. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13? 13 or 14? Oh, I can't handle it. Someone that has it done for them, tell me if that's right. Yep, Catherine? Okay. Okay, so converting between KP and KC, that's one we did at the end of class on Monday. Manipulating an equation. They're just kind of all rules involved in K. And then the last thing is not including solids and liquids. And maybe I shouldn't have just told you right away. Yeah.
Because when you're like manipulating an equation, like multiplying it becomes an exponent, if you divided an equation, would you have to take the log of K?
That is a very fascinating answer. No. Could you do, no, you're right. You might have to, because, no, you would just do to the 1/2. So if you were dividing it by 2, it would be raised to the 1/2. I was like, because logs bring the exponent in front of the expression. So no, you would raise it to the 1/2. Yes, not negative, because that would be the inverse. Okay, so on the last one, it's just asking you to write the K expression, not a value, just what it's equal to in terms of reactants and products. Okay, so biggest thing on these last two, recognize the first one, it's a KP. So you want to put it in terms of pressure. So it's the pressure of O2. There's a 3 in front of the O2 though, so it's the pressure cubed. We do not include solids or liquids, only gases and aqueous. So none of that potassium perchlorate, potassium chloride is included. And then in the second one, we don't include the water. But those are concentrations, so I'm putting it in the brackets to imply we need to do molarity. All good? Okay. All right. So let's do, we did both of those. I was going to say, let's do a practice problem with this. Okay. Just kidding. Let's move on. All right. Now we need to talk about what if we're not at equilibrium, because most reactions, you're going to put reactants together and they're going to make some products, or maybe you're going to have a mixture of substances that are reacting, and you need to know how are they going to react. And what I mean by how is in which direction, because the whole idea of equilibrium is that there's a balance point and the reaction is going to proceed either to make products or reverse and make reactants from the products in order to achieve that balance point. So for the first one, right now we've got all reactants and no products, and the K is 50. So remember, we can think of this as telling us that at equilibrium, there's going to be more products. It's product favored. Another way of saying that is that the forward reaction is kind of the dominant reaction between the two. The forward reaction is much more significant. There's another way of saying this. I don't know. I'll think of it. I'm sure I'm getting all the words out eventually, but just kind of slightly different terminologies. The balance point is further towards the products. So right now, if this is how we're starting, let me label these so I know which one we're talking about. So this is case 1. So in case 1, we are way towards the reactants. So we need to do this, right? So the reaction has to proceed in the forward direction and make some product. The second one looks like this, and initially you might be like, well, that's fine, right? Unless the K is infinitely large, then you have to have at least a little bit of the reactant, okay? So maybe it'll go like this, ever so slightly to the reactants, okay? So it starts here, and it goes like that. But it still needs to get to that balance point of a ratio of 50. Like 50 means 50 of the products over 1 of the reactants, right? So there's a little bit of a balance there. It's very heavy on the product side, but so I'm going to even to emphasize that, draw it as a little arrow. So it is going to go towards the reactants, but only a teeny little bit. The third one is maybe a little bit harder to understand. However, you're still saying, remember the K is equal to HI squared over H2 times I2. Well, if I2 is 0, it's still not going to be equal to 50, right? We have to have a little bit of both, every single species. Let's not even just say reactants. Every single compound, chemical, in the reaction, there has to be at least a small amount, unless the K is infinitely large or infinitely small. Okay, so we are going to still go in the reactant direction, so to the reactants, to make a little bit of that I2. Okay, so this is going to be the first step in any problem, any equilibrium problem that we do. We need to know which direction is the reaction going to proceed. Okay? So these 3, I repeat them here just because I think originally this was a single table and then I separated it. So We're not going to worry about that here. Anytime you have 0, you're going to have to go towards that thing to make some. But what about if you have all the things? So in case 4, we have H2, I2, HI. So how do I know there's kind of, is the reaction already at equilibrium? Or do I need to make it go one way or the other to get to equilibrium? Okay, so let's just plug these numbers in and see, do they equal 50? Because if they do, then that must mean we're at equilibrium, right? So I'm going to say 0.5 squared over 0.5 times 0.5. Hopefully you're seeing pretty quickly. This is just equal to 1. Okay, so we're not at equilibrium yet, right? We need to do something to get to equilibrium. Any guesses on which way the reaction needs to go to get us to equilibrium? Lily? Yeah, you have to make some product. Because the products are what's on top, right? Reactants are on bottom. So what we're basically saying, if we're saying that ratio is equal to 1, it means it's not big enough yet. We need to make it bigger. Well, the way you make a ratio like that bigger is you make the top bigger and you make the bottom smaller. So that means we need more products to be made. So the reaction is going to go this way. Okay, so this process of figuring out which direction it needs to go is actually a very formalized process in textbooks. We use the term Q for this calculation. So what I did there, right, was I just plugged into what the K should be, and then I saw, does it equal that? So the K, to be really clear, is only when it's at equilibrium. So I would say the concentration of HI squared, but just to emphasize that, that's at equilibrium. We're going to give a name to the same ratio when it's not at equilibrium. We're going to call that Q. And we can use Q at any point. It has the exact same ratio, products raised to their coefficients over reactants raised to theirs, but they're not at equilibrium. I just realized I left out the EQ there. So you plug the numbers in. If you're given amounts, you plug the numbers into that same ratio. They're just not yet at equilibrium, or at least you don't know if they're at equilibrium. The easiest, convenient answer would be if they're the same. If Q is equal to K, so Q is the thing you're finding out, it's just that ratio. If Q is equal to K, you're already at equilibrium and nothing needs to happen. It's not going to go in any particular direction. It's going to go in both directions, but it's going to be at the same rate, so you won't notice it. Yep.
Will there be a no answer option if for the value of Q if there are no reactants?
If there are no reactants, because it would be 0, and so then it would be 0 in the denominator. Yeah. So that's why I crossed out where it said value of Q. I was like, that's meaningless, right? Because let's see, if it's over 0, it's undefined, right? And if 0's on top, then it's basically 0. It's approaching 0. Yeah, so there is no real meaning to Q, because K and Q cannot be equal to 0.
What do you mean when 0's on top, it's approaching 0? If you have 0 items and divide it by, 5, you still have 0 items.
Yeah, if you think of it as something physical, yeah, I guess you're right. No, you're right. It would be if it's 1 over infinity. That's when you would be approaching. Yeah. Apparently, I'm really terrible at math.
I think you're just tired.
No, I think I'm just bad at math. No, I'm good at math. I'm just not good at the, definition-y kind of things. Like you give me like an equation and, you know, even like a complicated whatever, I can probably solve it, but I can't
Tell you why.
tell you why. Yeah. Or like name laws and stuff. Yeah. Okay. So in the example we just did, Q was significantly smaller than K, right? So Q was other way around, less than K. All right. And we said to make Q start to get bigger, because we need it to get bigger, right? We need the top number to go up and the bottom number to go down in order to get it closer and closer and ultimately to 50. So that means the reaction is going to have to go towards products. Okay, so let's do the next one. It's a bit of a spoiler alert, so I just won't say it. There's only really 3 options there of how Q and K could be different. So for number 5, go ahead and calculate Q and then determine which direction the reaction needs to proceed in order to get to equilibrium. Okay, so 56, is it 0.25 or was it 0.75? Okay, I was just remembering from last class, I didn't calculate it. Okay, so it's a little bit too big, right? The Q is a little bit heavy on products versus what it needs to be at equilibrium, which is 50. So it's going to have to use up some of those products, make reactants. Or another way of thinking of it, if we look up at this Q again, is that we need this guy to go down a little bit and these ones to come up a little bit to lower that value, get it closer to 50. So Q is greater than K. It's going to go to the reactants. Okay, so I summarized it up here, but it's also listed down here. Mathematically, that should make sense. If you don't want to like think through it every time, like, oh wait, I need this to go up and this to go down, so I have to go this direction. You can just like memorize this thing. what I always tell people is like, we always say Q versus K. Like we never invert it and say K versus Q, just how people talk, because the Q is the thing you're starting with. So it's opposite the way the less than or greater than sign is pointing. So if it's less than, it goes that way, not, the sign is pointing that way. Okay? All right, let's do one more example, and then we'll apply this to some real problems, or at least we'll start to talk about real problems. We might finish a little early because I don't want to push this too far beyond where my first class is. Okay, so this is very similar to the other one, just predict the direction that it should go. Yeah, 2 days is really too much for that. Oh, well. I think I mentioned this before, but if they don't tell you a subscript here, it's C. Concentration is kind of always the default. So this is the first step you're going to have to do every single time you approach a problem. You first need to know which direction is the reaction going to go. Because you can't like say, oh, I'm going to get rid of some of this and make that if you don't know which thing you're getting rid of and making. Okay? And there will be lots of times where we give you mixtures of things. Now, like I said, if any of the species in the reaction are 0, you have to go make some of that. And we're not going to do problems where the K is infinitely large or infinitely small, because then you would just do regular old stoichiometry. All right, good with this one? Okay. All right, so we're going to go ahead and go into the more complicated problems. And like I said, I only got to this one with my other class, but I kind of think we'll do a couple, just because then if we have extra time on another day, we can just use that for more practice instead of, do you love how I'm like, we're going to end early? Just kidding. Like, I never end early. I'm always pushing it right to the last minute. So, okay. So what we're going to do, we have these steps, and I'm going to walk you through how we do these steps in this next problem. We're going to use a thing called an ice table. Now this is very formalized. Obviously, when you're doing it yourself, it's not gonna look so nice and tidy. When I do it, I will just write the species down in the balanced equation, and then I will write ice, initial change, equilibrium on the side. And then I'll just put the amounts in here, 0.5, 1, 0, 0.15. So this one's given to you as a table. Lots more times, let me look at one where it's like given to you in wording. Oh, come on. Yeah. Find the amount of NO2 that must be added to 2.6 moles of SO2 in order to form 1.2 moles. So you're having to interpret from the words what's an initial concentration and what's an equilibrium concentration. What stuff do you have? And the ice table is a way to assemble those things, all those little bits of information together in a concise form. Okay, so that's the first thing. You're gonna set up your ice table, put in those different concentrations wherever you can. And then the second thing, so that's step one, the second thing is do the Q versus K and decide which direction the reaction is gonna go. So in this one, there's 0 of the product, so the reaction has to go towards product. If you had initial amounts, you might have to do a Q to find which way it would go. Every time I teach this, I think maybe it would make sense to teach regular old stoichiometry like this too. Like, no, because you don't know the ratios off the top of your head. I don't know. Anyway. Okay, step 3, define the change in terms of X. So what I mean by change, like let's pretend for a second this is regular stoichiometry. Let's pretend that the K is infinity, okay? It's really, really big. So the CO and the H2 are in a 1-to-2 ratio. So if that was the case, these are actually in correct stoichiometric ratios. They're nothing's in excess. So I would use up 0.5 moles of this and 1 mole of that, right? Because for every one of those, I use 2 of those. That's why it's twice as much. And I would make 0.5 of this. So that's where the 1-to-2 to 1 ratio comes up. That would be if the K was big. This would be regular stoichiometry, where all of those examples we probably gave you were for ones where the K was basically infinitely large. And in the end, so scrapping this, you would end up with none of this, and 0.5 of that. Right? That's what we have assumed in the past. So the way this table works is you're like saying, here's how much I start with, here's how much I use up of those guys. That's why they're negative. Here's how much I make of that one. And then the last line is like you're doing the sum there of those. Or difference if you're talking about that negative one. Okay? However, the K is not infinitely large here. We don't know what the K is. In fact, that's what the question is asking us, is what is the K? So we need to say, I don't know how much this change is. It's some amount. All that I know is that it's going to get used up on this side because I know the reaction is going to make products. And the other thing I know is the mole ratio. So for the CO, I'm going to take some amount off of that 0.5. For the H2, I'm going to take twice that some amount, so minus 2x. And for the product, I'm going to make that a little amount. Now, for lots of the problems that we're going to do, and I'm sure for the next one, yes, we are going to not know anything about equilibrium, but we are going to know the K. In this instance, we know what the equilibrium amount is. It tells us it's 0.15. So what does that mean X is? Knowing how this table works, 0.5 minus X has to be equal to 0.15. So that means X is equal to 0.35. So for whatever reason, we don't really know why yet, because we don't understand what the K is. Not all of that 0.5 gets used up, only 0.35 moles of it does. And it leaves behind 0.15 of the CO. So that's the equilibrium amount. So now that we know that, like we interpreted it from the table, we can go apply that to the other X's. So H2 is using twice that much, or 0.7. And so it's left with 0.3. And the methanol is that same mole ratio, it's that 1. So that means we're making 0.35 of that. So again, think of this line as equals. So now I can find the K, because K is equal to methanol over CO times H2 squared. And I can just plug in, these are equilibrium values, but that last line is at equilibrium. So now I can just plug those in. 0.35, 0.15, and 0.30 squared. And that is the, I was gonna say is the next step. I'm gonna say when you prepare the ICE table, you should probably also define K, meaning like set up the expression for K. Because you're gonna use it whether you're solving for equilibrium concentrations or solving for K in this case. Good? Any questions on this? Am I moving too fast? All right, let's go ahead and do another one of these. A little bit more complicated now, though, because we don't have any information about equilibrium other than the K. So in this one, the ICE table is already set up for you. Step 1, Q versus K. Well, boring. We have to make product because there's none of that to start. So now you go ahead and define the change. So like minus X plus X. And then I want you to do the sum for the equilibrium line as well. You're just gonna have to leave X in that sum. Okay, so it's gonna be more like an expression than a number. So once you feel like you've got that line for equilibrium, I'm going to go ahead and do what I said earlier about define the K. Like write the K expression. Oops. All right, so for those equilibrium amounts, all I can say is that the equilibrium is 0.2 minus x. That is kind of useless, right? Like, great. That doesn't give us a whole lot of information, okay? At least on NO, it's just 2x. Like, whatever we find out x is going to be twice that much. So here's how we're going to do it. We're going to plug in the equilibrium amounts into the K expression just like we did, but now they're going to be in terms of x. So it's going to be 2x squared. And on the bottom, 0.2 minus x times 0.2 minus x. And all of that's going to be equal to 0.1. So some of these are going to be pretty straightforward. Some of them are going to be very complicated and require you to use the quadratic formula. And some of them are going to be complicated, but we're going to be able to make an assumption that makes them super easy. Okay, so this one looks complicated. If you notice though, since these terms are equal to each other, another way to write this is 0.1 equals 2x squared over 0.2 minus x squared. So because of that, what I can do is just take the square root of both sides, and that'll make life a whole lot easier. I guess I'm just going to continue on to the next page. So this will be the square root of 0.1 is equal to 2x over 0.2 minus x. Okay, much easier to solve. So last few minutes, I want you guys to go ahead and do the algebra, because lots of times people are like, oh yeah, I can do that, I'm all good. You need the practice though, I guarantee. I'm just gonna write down what that one is because I like it to be in a number better. Okay, so the square root of 0.1 is 0.316. So go from there and solve for x. And I will do it along with you. For the first couple, just like as you guys are remembering algebra, if you haven't used it for a while, I will try to write like all of the steps that I'm going through. I can get pretty lazy myself if I'm doing this kind of stuff. But my daughter's in pre-algebra right now, so there's a lot of practice now that I'm like, oh, I need to actually show my work for her. If somebody else gets the same number as me, let me know. I'm gonna double check my work though. And then you feel like you're done, but you're not quite. So you just found out what X is? What does the question ask though? It says determine the equilibrium concentration for each species. Okay, well the equilibrium concentration is, it incorporates X, but that's not all it is. So I'm just gonna move this junk away. So we're gonna take this equation kind of form, and we're gonna plug in X, and then that will give us our equilibrium concentration. So 0.0273 is what X is. 0.0273. So the equilibrium concentration of N2 is, and of O2 for that matter, is 0.1727. And then for NO, it is 0.0546. So these problems are definitely involved. I think I'll still make the test just as long or just as many questions, because I don't want to, like, every time you reduce the questions, then like you get one wrong and it's a much bigger deal. But I think I'm going to give the test, even though it's not a final exam, I'm going to give it on the final exam time, which means you can have more time, so I don't have to like rush you through it. So these problems do kind of take a lot of time, right? You have to go through all these steps. Usually you're solving for X. Sometimes it could be a complicated algebra, and then you have to plug it back in somewhere. So it is going to take a significant amount of time. Thankfully, even though we're going to apply this to other stuff in chapter 17 and 18, those are... Oh, this is 16. This is not that test. This is unit 3. Okay, so I am going to have to be careful not to give you any really, really long ones. So I would say you'll probably only see like 2 of these on the test, but don't think that means you can't understand it, because there's going to be other stuff like, tell me the direction of the reaction or whatever. And they'll be worth more, because I can't include quite as many. Okay. Lots and lots of practice on Friday of this stuff, including having to solve the quadratic formula. Anybody need me to scroll down? I'm going to scroll down just in case. See ya. Lily, you look bothered. Did I do something wrong? I mean, I'm pretty sure I didn't in this instance, but I'm just checking.
I didn't realize that you square rooted it, and so I just kept it like with the exponent up there, and I got into I I was getting into the weeds of cut.
Oh gosh, you like actually squared them and was like
Yeah.
foiling
I
it.
was foiling it. I was
Oh,
like, wow.
because then
okay,
you
so-
really would have to do the quadratic.
Yeah, pretty
Yeah.
much. And I was like, oh, this is a lot.
And then you're like, wait a second. Yeah,
Yeah.
when I first saw this problem, I was like, I don't want them to have to do this.
Yeah.
But it's just a little fun trick.
Yeah.
I wanted a quick clarification on one
Yeah.
thing. About the signs of X.
Okay,
So,
yeah.
Because the first one, Q was greater than KC. Oh no, it wasn't. Okay, I must.
It's because it's 0. So we haven't done any yet where there's a non-zero one that we actually solved. It was only up here. So if you set up an ice table for this one, you would have to do minus x on that side. It would actually be minus 2x. And then this would be plus x, and that would be
And
plus
that's just
x.
because of the coefficients.
Yes. Yep. And the minus is on this side because you're going the opposite direction now.
Okay, and it's
Yeah.
the opposite direction because Q was less.
Greater than k. Yeah.
Okay, yeah, because you need more reactance.
Yes.
Okay,
Yep.
got it.
Good.
Thank you.
Yep.
What's up? How you doing? Good. How are you? I'm good. I'm good.
Aaron, hold my stuff.
Or is it a good thing? No.
Start going through it, look for the test answers.
No.
Obviously, it's
Which is fine, and you can talk about both sides.
And like a week,
Kind of like Noah's presentation.
a week from
Alright,
Friday,
yeah,
a week
there's
from next
just about
class.
access to that.
Sam, your hair looks fine.
It looks absolutely terrible.
It
In
does.
that manner.
Is that what you wanted to hear?
Stick you some business stuff.
I'll feed into it.
Yeah, it would be great if kids wanted to play hockey, to play, but, you know. I'd like to be in Major League Baseball too.
Shock yourself.
That makes sense. So the topic's good.
Why would you plug it into that one? It just did it actually just shock your ass? Oh my gosh.
Guys, look at all these posters.
What?
It's not working.
Literal things I always like.
Poster templates.
Oh,
They're so
What's
pretty.
that on?
I don't know, I just looked up poster templates online.
It is unplugged. Oh, okay.
I thought I saw that in my other hand.
Marta, do you want me to plug it into the one that's right behind Sammy that's not broken?
It's okay. I think I have enough.
Okay.
Oh my gosh.
I plugged my phone in there once and it was fine.
Wait.
Your hair's gonna look really bad now. It's gonna be sticky straight up.
I had balloons at CCO.
Had what?
We had balloons at CCO, and we were blowing them up. And my hair popped out. I had just washed it, and it was like,
I really fire hazard.
Why? What is it?
You just gotta like Sammy just almost died plugging something in.
Oh my gosh. I swear that happened in my house once too. And I was like, the guy who owned it before us was like Mr. DIY. And I'm like, oh my gosh, did you DIY the electric? Like, that's terrifying. And every time I plug into this one outlet, I feel like I get shocked. Was that what happened?
Yeah.
Yeah. Yeah. Okay. That is freaking me out a little bit. That is like the one thing. I'm like, you should never, nothing that has to be like significantly weight bearing and electric.